Hello, I'm Barbara Spiecker, a postdoc working with East and White at the University of New Hampshire. We've been working with PrEP to figure out cost-effective ways to monitor the Great Bay. We know the importance of long-term monitoring in ecological research and management cannot be overstated. Ideally, these programs should be robust, providing the necessary evidence to guide management decisions. However, we're all aware that resource fluctuations, evolving objectives, and unexpected events can throw a wrench into the effectiveness of these long-term monitoring endeavors. Today, we're diving into the nitty-gritty of the Great Bay to explore whether we can trim down the sampling effort without sacrificing the valuable information gleaned from our long-term surveys. All right, let's get to it. In today's talk, we're on a mission to figure out the perfect mix of sites and years needed to catch those crucial ecological trends in the estuary. Not only that, but we're also diving deep into which sites reveal the most information. Now, the real star of the show is the methodology behind answering those burning questions. I'm going to walk you through it, giving you a sneak peek into how you can take your data and work some magic with the methods. The end goal is arming you with the knowledge to make choices in your research, management strategies, and overall understanding of your your ecosystem. Let's roll. All right, let's break down the first piece of the puzzle. What's the minimum number of sites we need to keep our eyes on? And which ones do we not necessarily need to keep our eyes on? Let's unveil the secrets in these hidden sites. We can crack them by performing a spatial sampling reduction. Let's use 10 sites as an example. We'll randomly divide these sites into 10 groups. From our 10 sites, we're going to remove one site and set the remaining sites aside and call that our reduced data set. And then we'll repeat the process, removing one site at a time until we've gone through the entire group. We'll have 10 reduced data sets in total. Then we'll continue the site elimination process, but this time we'll repeat the procedure with 20%, 33%, 50%, and 66% of the sites removed. For each of those reduced data sets, we're lining them up against the full data set. The goal is to calculate the overlap and see where they sync up. Let's circle back to our first question about the minimum number of sites. Take a glance at the figure on the right. Using water temperature trends in the Great Bay as an example, the x-axis shows the reduction in sampling effort, or the percentage of sites that have been removed, while the y-axis reflects how much these reduced data sets match the full model. What stands out here is the more sites we remove, the less they capture the long-term trends. We know that life is about finding balance. Even in long-term monitoring, we're juggling between cost and information density. At a standard 95% confidence level, removing 33% of sites dips us below that threshold. But remember that 95% is not a one-size-fits-all. Your acceptable error level should be tailored to your situation. So the number of sites that you can afford to lose depends on your chosen confidence level. It's all about striking the right balance. Now let's shift gears to the second question, spotting the sites that aren't bringing much to the table. We're taking it step by step, removing one site at a time and checking which one has the highest overlap with the full model. Essentially, it's a way of saying this site isn't adding a lot to the long-term trends. In the details, all of these sites might align with the overall trends, but for example, Adams Point with the highest overlap offers the least useful temperature information. Great. So we wrapped up the spatial side of our analysis. Oh, dead mic. I guess a second.
ask a question in the meantime? Or is that not?
Sure.
You just said, had the most amount of overlap, so it's least useful. My brain sort of hooked on that. You stated that correctly?
That's correct. Yeah, we want to see that they're most similar, meaning that they're not necessarily adding much to the long-term trends. Right? So if they're removed, we're still having that important information there, or you're not removing any useful information. Does that make sense?
Yes.
Thank you.
So we just, excuse me, so we've just wrapped up the spatial side of our analysis. Now let's shift gears to the temporal aspect, figuring out the minimum number of years that we'll need to monitor. We've adopted a temporal sampling reduction strategy where we slice our data into intervals of, say, 3 years. First, we take a subsample of the first 3 successive data points and then calculate the slope. We shift the window by 1 data point and calculate their slope, and then rinse and repeat. Expanding our approach, after the 3-year subsamples, we'll do the same operation for 4-year subsamples and beyond until we've reached the full range of years in our data set. With each X-year subsample, we're taking a peek at the slopes within that group and then comparing them to the long-term slope. We're comparing using 2 criteria, the first being direction, and checking if each slope aligns with the long-term slope, whether it's positive or negative. The second criteria is magnitude, and checking if each slope falls within 1 standard deviation of the long-term slope. And here's the key part. If 80% of the slopes with those X-year subsamples match both in direction and magnitude with the long-term slope, we've got our answer. Those minimum X-year subsamples meeting the 80% criteria become our go-to for the minimum number of years to monitor. Now, looking at the Great Bay environmental data, we figured out the minimum years to monitor for each variable across all sites. Check out the table on the right. It highlights 2 thresholds, the minimum years with 80% of slopes matching the long-term slope, and the minimum years that have 100% match. Some variables show surprisingly low minimum years, ranging from 3 to 5 years. This might be due to low variability within the data, either a constant long-term trend or a strong unwavering trend over time. For those curious minds eager to delve into the minimum number of years for each variable at each site, snap a photo of the QR code in the right corner. It'll give you more details on the site level trends. In the QR code, you'll find figures like these. They're outcomes of cluster analysis. On the left, the figure pinpoints where water temperature is monitored at different sites, each marked with a color. Matching colors means similar trends, while different colors represent distinct trends. The number by each site tells you the recommended minimum number of monitoring years. On the right, the dendrogram shows how clusters are related. Look at the height where the clusters join. Shorter links mean more similarity. This is like a visual guide to understand the connections between data clusters. And there you have it, the grand finale of our little chat. The bottom line, figuring out the sample minimum, be it years or sites, is like finding the perfect recipe. It's all about your acceptable error threshold. And guess what? We have the secret sauce, the code to work those numbers, which is exciting, right? But the fun part is it's not just a one-size-fits-all deal. It's a personalized journey just like picking your favorite ice cream flavor. So whether you're into vanilla or rocky road, we've got your back. Please reach out to us and let's chat. We're here to help you sprinkle some magic on your data and tailor the information you need for your program.
Great, thank you so much, Barbara.